My dear students, welcome to the series on mathematics. Today we are going to look at implicit differentiation that you will be studying at grade 12. You all know that equation of a curve up to now has been written y is equal to fx, where y is the subject of the formula. However, not all curves can be written explicitly like that. This is called an explicit equation of curve. Why explicit? Because you have made y subject of formula. Now, you have implicit equation of curve. For example, x squared plus 3xy minus y squared is equal to 5. As you see here, this is an implicit equation of curve, whereas this one is an explicit equation of curve. Now, as you know, as you have been working with curves for several years now, the question that you will be asked is, find the gradient of the curve, find equation of tangent to the curve. So what are we going to look at in this unit? We are going to look at how to differentiate this equation. So how do I differentiate x squared? Of course, you know when we differentiate x squared, we get 2x. How do we differentiate 3xy? How do I differentiate y squared? And obviously, you know how when we differentiate 5, we get 0. So, let's go back to the basics. When you differentiate x squared with respect to x, you get 2x. When you differentiate x squared with respect to x, you get 2x. Have you ever thought, if we had asked you, if you differentiate x squared with respect to x, you get 2x. Have you ever thought, if you had asked you to differentiate x squared, but this time with respect to t? What will the answer be in that case? Will it still be 2x? No, it will be 2x dx by dt. In fact, we ought to have told you that when you differentiate x squared with respect to x, it ought to have become 2x dx by dx, because you are differentiating a function in x with respect to x. So, when I differentiate x squared with respect to t, I will get 2x dx by dt. So it's very important for you to understand that. Now, if I ask you to differentiate y squared with respect to x, what would you get if you differentiate y squared with respect to x? 2y dy by dx. If you differentiate y cubed with respect to x, you get 3y squared dy by dx. Of course, terms like 3xy, if I ask you to differentiate 3xy with respect to x. It's a product. Since a product, we're going to use product rule. So what will it become? I keep 3x as it is, I differentiate y. Differentiate y with respect to x. Plus keep y, differentiate 3x with respect to x. So what does this give me? When I differentiate y with respect to x, it's 1y. So I'm going to get 1 dy by dx. If I had to differentiate 2y with respect to x, I would have obtained 2 dy by dx. So here, y, differentiating y with respect to x gives 1 dy by dx. Here, differentiating 3x with respect to x, it's 3. We ought to have written dx over dx, but we are not writing. It will be equal to 3. So it is 3x dy by dx plus 3y. So we apply here the product rule to differentiate a product. So let me take an example. If all these examples set by CIE, the equation of a curve is ln xy minus y cube equal to 1. Find dy by dx. So, obviously, this is an implicit equation of curve. Therefore, I'm going to use the technique we learned earlier. But before that, there's a trick in the question, ln xy. So we are going to use the property of logarithm to write ln xy as what? Ln x plus ln y minus y cube equal to 1. Let us now differentiate with respect to x. Differentiate ln x. What will I get? 1 over x. Of course, I should have written dx over dx, but it is 1. Differentiate ln y. 1 over y. Here I'm differentiating a function of y with respect to x. So dy by dx. Differentiate y cube. So this is 3y squared dy by dx. When I differentiate 1, I get 0. Very common mistake for a student to forget to differentiate the constant on the right-hand side. I'm now going to make dy by dx the subject of formula. So, 1 over x here will go on the right-hand side. I will have dy by dx 1 over y minus 3y squared. So I had two terms having dy by dx. I factorize dy by dx, so 1 over y minus 3y squared is equal to minus 1 over x. So dy by dx 1 over y minus 3y squared equal to minus 1 over x. The LCM gives us y minus 3y cube equal to minus 1 over x. Dy by dx, transferring this term on the other side, will give us 1 over x, y, 1 minus 3y cube. or y 3y cubed minus 1. That's dy by dx. We'll take a second question. A curve has equation x cubed minus x squared y minus y cubed equal to 3. Find dy by dx. And second, equation of tangent at 2, 1. So, let's do it together. Differentiate x cubed. What will I get? 3x squared dx over dx. I won't write it. Here it's a product. So I keep x squared, I differentiate y. Remember in the previous example as well, we differentiated y. We obtain 1 dy by, if we had 2y, we would have obtained 2 dy by dx plus, keep y as it is, differentiate x squared, 2x dx over dx, we won't write it. Differentiate y cubed, 3y squared dy by dx. Differentiate 3, so it becomes 0. We differentiated x cubed to obtain 3x squared. Keep x squared, differentiate y is 1 dy by dx. It's a product rule, so plus, keep y, differentiate x squared, 2x. We had a minus here. Differentiate y cubed, 3y squared dy by dx. Differentiate 3, we obtain 0. So what are we going to do now? We are going to simplify this term and make dy by dx subject of formula. So first term I had was 3x squared minus x squared dy by dx minus 2xy minus 3y squared dy by dx equal to 0. And as usual, we are going to make dy by dx subject of formula. If you want, we can multiply everywhere by minus 1. So this is minus 3x squared plus x squared plus 2xy plus 3y squared dy by dx equal to 0. These are the two terms having dy by dx. X squared plus 3y squared. We transfer minus 3x squared on the right-hand side. We transfer this term. Therefore, dy by dx becomes 3x squared minus 2xy over x squared plus 3y squared. That's dy by dx. We were asked to find dy by dx. Now, the second part, we are asked to find equation of tangent. What is equation of tangent? Equation of tangent is y is equal to mx plus c, where what is m? M is equal to dy by dx. 3x squared minus 2xy over x squared plus 3y squared. We are told to find the equation of tangent at the point 2, 1 What does the point 2, 1 mean? I replace x by 2 and y by 1. X by 2. So here I replace x by 2, y by 1. Replace x by 2, y by 1. So, remember 2, 1, x equal to 2, y equal to 1. So this gives me 3 times 4, 12. 12 minus 4, 8. 4 plus 3, 7. So the gradient is 8 over 7. Equation of tangent, 8 over 7x plus c. Replace by 2, 1. Replace x by 2 and y by 1. Right, this gives c to be 1 minus 16 over 7. So, this gives us minus 9 over 7. Hence, equation of tangent is 8 over 7x minus 9 over 7. So, in this example, we have shown to you how to find equation of tangent, how to differentiate the implicit equation of curve, and then using the usual technique to find equation of tangent, y is equal to mx plus c, we have been able to find the equation. Of course, there are certain equations, certain questions that will ask you, write the point where the tangent is parallel to x-axis. If the tangent is parallel to x-axis, and you know x-axis is horizontal, horizontal lines have 0 gradient, so we would have equated that to 0. Of course, when we equate that to 0, do we get a number? No. When we equate dy by dx to 0, we get an expression. This expression and the equation of curve must be solved simultaneously in order to obtain the point where the tangent would be parallel to x-axis. The same question. Find the point on the curve where the tangent is parallel to y-axis. Y-axis is vertical. Therefore, the gradient is infinite. So in that case, what will I do? I will equate the denominator of dy by dx to 0. Because when the denominator is 0, dy by dx will become infinite. So again, I will not get a value here when I equate the denominator to 0. I will get an expression. I'm going to get an equation here. I'm going to solve this equation with the equation of curve simultaneously. Just as in the previous case, we would have solved the two equations simultaneously in order to obtain the coordinates of x and y. So, my dear student, this brings an end to this part on implicit differentiation. We are going to look at next the parametric differentiation. Until next time, it's goodbye from us.